today we are going to begin the frame type foundations. Now for frame type foundations, our pedagogy will be more on the practice. So the concepts you have learnt for the block type for foundations. So essentially the concepts are more or less same. The only difference is the analysis part. So we'll just study some of the aspects of the frame type foundations, and then we'll do practice. So here the theory part will be less. Now the frame type foundations, they are basically provided for medium or high frequency machines, rotating machines, and typically all the turbo generators. For example, if you visit any NTPC plant, you will find turbo generators. So they all are seated on these frame type of foundations. So the essentially this kind of foundations, they look like 3D frame type of structure, just like for the case of the buildings. The only difference is that these are extremely heavy. They are, if you find the member sizes, you will find that the member sizes are very large: columns, the beams, the slabs, and also the foundations. So typically they have raft type of foundations below. So most of the these turbo generators in power plants, they are resting on these frame type foundations. But why do we provide frame type of foundations for these machines? Earlier the type of foundation which was provided was wall type foundations, and now the modern approach is to provide frame type foundations. So frame type foundations, they provide a number of advantages. So we'll just see what are the advantages of the frame type of foundations over any other system. Now these machines, they are extremely powerful machines and they exert very high forces. So if we were to provide block type foundations, it will be highly uneconomical. So that's why the frame type foundations, first advantage is that they provide a saving in terms of the space and savings in terms of the materials. So that is one aspect, because otherwise the volume of the concrete would be huge. Alright. So secondly, because we are providing frame, so frame has lot of openings, so this provides a greater accessibility for servicing of the machine also. So typically there is a platform also, so operators and service personnel, they can just climb and they can just walk over it, they can access any part. So these kind of advantages are there. And then they are structurally better, because this is a beam column frame type of system. So they are structurally predictable. Their behavior can be analyzed using the available methods. And besides that, because we are providing frames and we have very heavy raft also, so they show less problems of cracking, less settlement issues, and also they don't suffer so much thermal effects. Otherwise, if the foundation size is huge, then you can expect that the thermal stresses, because heat has difficulty to dissipate, so they will have thermal issues also in the case of the very huge foundations, because there is no escape route. Here there are openings and there are gaps between the members, so the thermal effects, they are easy to dissipate. Now we just see how this foundation looks like. So we are just drawing first the plan. So in plan, the foundations, they look like any other beam column frame system. So just bear with this when we are drawing the shape. So typically we have the slab visible from the top and also the columns and the beams. So just like any other frame type of structure appearing from the top, now we are drawing the columns and the beams. And after we complete the plan, we'll also show you the elevation. The only difference as compared to the normal frames is that the sizes are exceptionally high, and then for the design we use the working stress method of design. So you can see that we have the beams and we have the frames in both the directions, and now we are drawing in plan the raft. And after we complete the plan, we'll switch over to the elevation, then it will be clearer. And now let's see it in elevation also. And after we complete this, then we'll show you the picture of an actual RC frame type machine foundation. So we are beginning with the top slab. So we are showing the cross beams. So all these cross beams, they are visible in this section, and then we are also drawing the longitudinal beam. Longitudinal beams, they are running two longitudinal beams, this one and this one. And typically what you find here, there's a haunch kind of construction. So there is a small overhang, though overhangs they are discouraged, large overhangs they are discouraged, but usually these slabs they are extended a little bit outwards. And now we will just draw the columns. So here, this particular structure, it has 8 columns, 8 large size columns. So columns are very important, so we'll just show these columns in the elevation. So basically we are drawing the section from this plane. So that's why we have the longitudinal beam and the cross beams visible as shown. So now we are drawing the columns. And the purpose of drawing this is that we will also make you familiar with the terminology. So there are specific terminologies associated with the various parts in the case of the frame type machine foundations. Now we are drawing the foundation block. So foundation block is supposed to be very massive, very massive. We'll just see later on in the clauses of IS 2974 part 3 also that the raft has to be very massive and very stiff. So that's visible to you that it's very thick raft, and compared to the raft, the columns, they look a bit slender, but columns themselves, they are very massive here. So let's now label various parts, and some of the terminologies here are a bit different as compared to the normal RC frames. So this raft is called as the sole plate. So this is the technical term used for the raft. So raft has to be there, we cannot provide isolated footings. So then we have all the columns. So columns are normal with reinforcement, only difference is that they are to be designed by the working stress approach. And then we have this longitudinal beam is visible. And then the cross beams. Now the deck slab, the top slab, there is a terminology for this, that this is also called as basically upper plate, or we can also use the term table for this, because basically it serves the purpose of a table where we are fixing the machine. So finally, the most important component of any power plant is basically the turbo generator or the machine. So usually the machine or the turbo generator is anchored, and these anchors, they must pass through the beams. So usually the beams, the cross beams, their locations are chosen so that anchorage points, they are lying on the beams. So we are drawing the location of the machine in the plan also. So basically it's positioned such that the load is being rested on the cross beams, and we are now showing here the 4 anchorage points also. So now this is how in real life situation the deck and the entire system looks like. So it's a very massive structure. So here you can see the machine, also the turbo generator. So I'm just pausing the video here. So what you can see here, the shape is such that it supports the machine. The bearing points and all those locations, they are predetermined in design, the data provided by the manufacturer, and it has a lot of utilities also, so that the machine can be serviced. For example, you see a lot of the secondary structures. So all these secondary structures are as per the design of the machine, because machine needs to be serviced also in between, machine needs to be brought and it has to be placed. So basically the entire structure is designed in such a way that it aids in the process, and there are a lot of cutouts also, so that servicing etc. can also be done. So it looks like a typical multi-story building. Now what we'll study today is some of the special design considerations. So we are basically just covering some of the design considerations which are there in IS 2974 part 3. So we just see what is different here as compared to the block type foundations. So some of the provisions are different, and you may find that some of the clauses, they have different considerations as compared to the block type foundations which you have already studied. And after we finish the main study, we would go and we'll also scan through IS 2974, just like we have done with IS2974 part 1. So we'll do scanning with IS2974 part 3 also. So first of all, these frame systems, they should be isolated from the main building, because these are housing very highly vibrating structures. So it's very important that they should be isolated from the rest of the structure. So special isolation should be done in terms of trench barriers and gaps, expansion joints. These should be provided as separated from the main structure. So these base raft should not be continuous, it should be aloof. Then when we are doing the proportioning, then we should do or proportion the members such that we don't face the problems of stress concentrations. For example, if we have sharp corners like this, so there would be stress concentration, and especially in the case of the dynamic environment, this could be bit harsh on the structure, so crackings etc. could be there. So this is the correct way, that we don't provide these kind of sharp discontinuities. So haunches, they are very common in these kind of structures. So the advantage is that there is less cracking, and also there would be higher stiffness of the joints, because we are providing extra thickness to the beams and the columns. So another important suggestion is that we should avoid large size overhangs, because these structures, they are vibrating. So we have already studied, and we have done examples also in the case of the block type foundations, that overhangs, they are sort of separate components, and when they are vibrating, they produce inertial forces, and especially here the frequencies are very high. So here the inertial force effect is very high on the critical sections. Therefore we should limit overhangs. Little bit overhangs, they are necessary as far as the requirements are concerned, functional requirements, but we should avoid large overhangs. Small overhangs, typically say 300 mm or 500 mm, they are fine, but large overhangs, say 1 meter, 2 meter, something, that should be avoided. Otherwise there would be very high inertial forces, and the design would be uneconomical. Now we are coming to the base slab. Now we have already emphasized that base slab should be very rigid, and at the same time it should be very massive, because we want that the vibrating mass should be very small as compared to the overall mass. So we should ensure a high degree of fixity of the columns with the base. So typically, as compared to the base raft, the columns might appear to be very slender, and if you visit any plant, you may not be able to see the base also, because base is underground. So if we see the thickness of the base, we denote the thickness of the base slab by TB. Then there are some guidelines as per IS 2974, and also some of the guidelines are as per the normal suggestions in the books. So why we emphasize on very thick and very stiff raft is that the condition of fixity, it should be realistically obtained. Otherwise, if the columns, they are heavier, then they may not show or exhibit the full fixity. So it's very important that the thickness of the raft should not be less than certain minimum thickness is specified. We'll just see one by one. First of all, the thickness should be higher than the width of the columns. and it should be at least 1/10 of the span of the slab. So for obtaining what is the span, what we do, we find out the average. We use averaging and find out the average span. Then it should not be less than 2 meters in any case. So imagine 2 meters of the raft. And then there is one more empirical relation, that it should be greater than 0.07 times the span to the power 4/3. So as we have already told, basically L is the average of the two adjacent spans. So here we basically make use of the clear span. So two adjacent clear spans of the slab, so that is counted as the slab span L to be used in these computations. So it's very important that the stiffness of the slab should be much higher as compared to the combined stiffness of all the columns. So if we just calculate EI by L of the slab, so that should be at least 2 times the EI by L of the columns combined. Next is the weight. So the slab should be very massive, so it's very important that the weight of the base slab should be higher than the weight of the superstructure and combined with the weight of the machine. So again, this is there so that the entire system is very massive. So we are countering the vibration forces with the high inertia of the base. These machines, they generate very high forces because the force is proportional to square of the frequency. Now as far as the location, the beams, they should be located such that they are just supporting the weight of the machine directly. So all the loading points where the forces are being exerted, they should not be on the slab, but they should be directly on the beams. So we must at the time of the planning stage itself, we must locate the beams such that the loads are directly, the loading points, they are directly on the beams. So eccentric loading should be avoided. And then the location of the loads, that should pass through the CG of the base, as for the case of the block type foundation. So if we have the centroid of the base, so the vertical line along which the forces are passing, the net force is passing due to the machine, so that should pass through the center of gravity of the base. So all the vertical forces due to machine, including the dead loads, they should pass through the CG of the base slab. Now here, because fatigue is definitely there, so fatigue was there in the case of the machine, the block type machine foundations also. So here a fatigue factor of 2 is used. Now this is different as compared to the block type of foundations, that here we are using less fatigue factor as compared to the block type foundations. Now here we are using frame type of construction with very careful analysis because here the structure is more predictable, the behavior is more predictable as compared to the block type foundations, where the effect of the soil plays very important role. But here basically we are providing very stiff base slab, so here the behavior is more or less predictable. So what we are doing is that we have the upper frame resting on very stiff base. So here the presence of the slab, that basically makes the effect of the importance of the soil much less. So that's why here the fatigue factor is less. So I think I'll just stop here and I'll come back to you for any interaction. So I am just unsharing this screen for the time being, and now you can all unmute yourself. So now I have allowed you to unmute. So you can first of all give me your feedback. Was there any interruption? Was there any interruption?
No, your voice was quite audible. And then,
okay, fine, thank you. But even if there was any interruption, I have recorded the whole thing, and it will be available very soon. So now you can raise your hand for any questions, because now we have reached part of the course where we want to emphasize more on the practice. And usually my courses, I make sure that people are not heavily loaded towards the end. So in my courses I cover the most difficult parts earlier, and now we have sufficient time to practice. So the analysis part will not be as complicated as in the case of the block type machine foundations. So block type machine foundations, there are very tedious calculations involved, but here we'll be using the stiffness approach to analyze. So what I'll be sending you an email on the instructions of how to install STAD version available with IIT Delhi. So I'll be sending you in the your courses group. So I hope every one of you are checking your IIT email. So on Friday we'll continue the main important points related to the frame type foundations, and once we complete these important points, we will just start the practice. We'll start the computational experiments. We will give each one of you problem, so that you learn the analysis with practice, because this is a professional course. So here you should get a feeling of the course. So at least the computational part you can feel, but when we conduct the course in person, that time all the students, they get well versed in all experiments. They get a feeling of how the vibrations are happening. We take them to the site, we take them to these air handling units within IIT Delhi itself. There they do measurements, they feel the vibrations, and they get experience. So in the end we also take them to the NTPC or similar TG plants. So those things we could not do, but at least the computational part you should get a feeling. And as far as the vibration related experience is concerned, I would advise that if possible, try to visit some plant near your homes, so that you get some feeling about these machine foundations. So you have any questions on today's talk? Please raise your hands. I hope my voice is not breaking now. Major Mehra, are you there? Major Mehra, can you hear me properly?
Yes, sir.
Okay, so during the main lecture, was there any issue?
So your video was not continuous, and in between, sometime your voice also breaks.
Okay,
So I'm
okay.
waiting for your recorded video.
In between, there was some problem. Okay, I got the feedback, so don't worry. I'll be uploading the video soon. So don't worry on that.